Tim Hyatt with the Skagit River Systems Cooperative is going to introduce some tools for helping prioritize restoration actions and work he's done with that in the Skagit Valley. Tim is a riparian ecologist with the Skagit River Systems Cooperative, a tribal natural resources organization. He holds a master's degree in forest ecology from the University of Washington and has nearly 30 years of experience in watershed assessment, fisheries, and riparian research, instream restoration, and habitat protection. His current efforts are focused on stream restoration modeling and GIS evaluations of riparian function. This presentation will describe two riparian function models, one for stream shading and the other for large wood recruitment potential. The combined models depict where riparian zones are currently most lacking and where riparian restoration will have the most benefit.
So I feel pretty strongly that this is just a really great opportunity to share ideas among practitioners and watershed professionals, get a little cross-fertilization of the ideas. And thank you to the conference organizers. I know this wasn't easy. I'm very honored to be invited. So this is some work that I've been working on for a few years now, mostly off and on part-time, but it involves trying to evaluate riparian zones throughout the Skagit Basin. The goals were to come up with some products that would help folks like you, the practitioners, better prioritize habitat and places for restoration. And secondarily, to come up with some tools and methods that were accessible and to other basins where they could pursue some of the same measures. So early on in this work, it became painfully obvious that there's really no point in trying to do riparian analysis in detail without better hydrography. The hydrography that we have available in the Skagit, mostly from the National Hydrography Dataset, but also from other sources, often has very misaligned streams. The stream arcs don't align with the actual location of the stream. This is a problem if you're trying to point out or analyze riparian vegetation and that vegetation is up on the side of the hill somewhere. It's even more of an issue down along the mainstems where the channel polygons are quite outdated and probably never were all that accurate. And it doesn't help anything to point out that these cobble bars really don't have trees that provide shade to the stream when they're cobble bars. So the first part of the effort, and it was to come up with better hydrography, and that was a very long and process. And that is its own presentation, and I'm going to skip over most of that and in the interest of getting right down to the part about the trees. But I need to kind of set the context on how we came up with some of this modeling. So there are a lot of advantages to updating the hydrography, two of which you're going to see today. Accurate estimates of riparian shade and wood recruitment. It's also quite useful for fish distribution maps, fish distribution modeling, and thus analysis of the habitat upstream of blocked culverts, and stream temperature modeling, and probably several other good projects that you folks could think of yourselves. So we're not the only ones to want better hydrography. 5 or 6 years ago, Skagit County started off by updating the hydrography in areas that were under the jurisdiction of the Voluntary Stewardship Program, that is in the agri NRL and rural residential NRL zones, which is pretty limited, but as it turns out, that was quite useful because they were working down off aerial photos and LiDAR, mostly hand digitizing, in areas that are quite flat, and the ditches flow both ways sometimes, and they covered areas that don't work well at all with the LiDAR derived hydrography that we were pursuing. So what we were more interested in were the headwater streams and the middle sized tributaries, the anadromous zone. In this case, this is a Cold Spring Creek, for those of you who know it. The NHD line is basically going up the ridge between two streams, and we were a lot more interested in mapping fish habitat. The orange is coho, and the thin blue line is resident fish habitat. And we were pursuing this LiDAR derived hydrography to do some of that. We can only do that where we have LiDAR, shown here. And we had a good LiDAR from the USGS Volcano Observatory for Mount Baker and for this for Glacier Peak in this nearly invisible dark green outline. And then we had the Skagit Flats. And then Washington DNR, after the Oso landslide, got some funding to do hill slope stability modeling. And they were going to do a lot of the Skagit, but only the hill slopes. They weren't going to do the valley floor, which is obviously the part we're keenly interested in. So the Swinomish tribe kicked in $100,000 and Skagit County kicked in 50 grand. And we were able to draw a map with these really funky boundaries that cover the anadromous zone and the riparian zones around them. And we were able to get that flown and then amalgamate all these different layers. And where we didn't have LiDAR, we used up here in the headwaters, we used the USGS 10-meter DEM so we would get a consistent basin area throughout the watershed. So working basin by basin, and like I said, I just skipped over a whole nother presentation. We did the single thread hydrography for the whole basin, and since then, including the area around Ross Lake. But again, in the areas covered by the 10-meter DEM where we didn't have better information, our combined single thread hydrography now incorporates the NHD in those areas that didn't have LiDAR. So what we were trying to do, we set the threshold to try and mimic the streams you see on a 7.5-minute USGS topo map. And we've now got, including the Ross Lake, we've got single thread hydrography everywhere, including the anadromous zone shown here in orange. Now that's single thread. To do riparian analysis, you also need channel polygons, which are also difficult to do, but LiDAR really helps a lot with this. Again, there's no point in trying to analyze riparian zones if you don't really know where the edge of it is. So using digital elevation models instead of heads-up digitizing, using what's called a relative elevation model to delineate some of these areas. The relative elevation model, every pixel in the DEM is not the elevation above mean sea level. It's the height or the elevation above the channel at that point along that transect. So what it does is it flattens out the longitudinal slope in a reach, removes that slope. It also gives you this really intricately detailed floodplain image that is just fascinating to look through. But analytically, you can extract from that relative elevation model contours that tend to follow the stream banks where there is a bank. And then by a lot of cutting and pasting and a little bit of interpretation, you can string these contours shown here in green into something a little more, into a coherent channel polygon shown here on the left. And that's a good start on a place for your riparian zone to begin. Notice that none of that could have been done with aerial photo interpretation because the overhanging veg completely obscures most of the water, nor is this a depiction of the wetted width. It's taking into account the cobble bars and basically trying to, something analogous to a bank full width, but mostly concerned with trying to define the edge of the riparian zone. So where we didn't have, so we currently have these channel boundaries for the whole anadromous zone and then some, up to the major tributaries up to about 20 meters bank full width, and a few down to about 20 feet bank full width, where those channels are really well behaved and the channel banks are really well defined. It doesn't work very well. The relative elevation model doesn't work very well on steeper reaches and cascades. What we have is the whole anadromous zone. It includes a lot of side channels. It separates out the channel islands. There's a separate layer for lakes, ponds, and wetlands that are connected to the anadromous reaches. It is so far incomplete, but it's coming along pretty well. It does not match up very well with the hand digitized from aerial photo stuff, but it does cover the smaller creeks a lot better. In areas where we needed a polygon, but didn't have those relative elevation model polygons, I used an equation to predict channel width based on precipitation, upstream area, and slope. This is from a paper that Tyson Waldo and I did a long time ago. When we were doing the single thread hydrography, we also, Gus Satius took the first stab at this, predicted widths based on another paper by Jeremy Davies and folks at NOAA. The two come out pretty closely, but what I'm showing you today is based on the Hyatt width, which was done first, done earlier. And here's a graphic example of where those worked on the swaddle. The major open channel areas were done with the relative elevation model, and also the back channels and the sloughs and the side channels, which wouldn't respond well to an equation based on watershed area. But in the tributaries that do respond to those formulas, those I created a polygon based on that channel width. So we've got polygons that cover the whole area. The reason that's important is that when you try and buffer out from a single thread, your buffer includes a lot of water. So using some vegetation data shown here in this green from Kim Pierce's high resolution land cover, and comparing buffers off of a single thread channel, a 20-meter buffer either side, and then buffers coming off of a channel polygon, 20 meters on either side, you see that what's encompassed here is a lot of water and not nearly as much land. Whereas here, even though a lot of the land, which is in desperate need of riparian planting, even though it's bare, because you're encompassing so much more land and less water, in these two examples, there was a doubling of the amount of vegetation in the riparian buffer. And if you're trying to prioritize your planting sites, it seems like good objective data on where they're lacking and where they're not is probably where you want to start. So using these buffers, and here's the beginning of the large wood model. Within the buffers, I used a all canopy, all return point cloud to develop a canopy height model within the 150-foot buffer. I also did it with a 300-foot buffer, but I'm going to show you the 150-foot results, and the reason will be obvious here in a few minutes. But within the 150-foot buffer, you've got tree heights, and everywhere else you've got bare earth. And then using the same buffers and the distance from the channel of each pixel from the channel edge, you've now got heights of edge and the distance from the edge. And the metric I want to use is the height distance ratio, on the theory that the larger trees closer to the stream are going to have a higher height distance ratio. They're going to be able to contribute more wood if they fall towards the stream. Whereas the smaller trees further from the stream are going to have a height distance ratio of less than 1. And these would not be able to contribute any wood, even if they fell directly towards the stream. Now, I'm not trying to model how much wood falls in the stream or collects in the stream. I'm not trying to model which trees are going to fall towards the stream. I'm actually not even modeling individual trees, as some folks do. I'm basically looking at pixel by pixel, what are the areas that are not capable of contributing wood, even if those trees fell towards the stream. So that's the map here. And we have that for the whole Skagit. What you're seeing here and what you're going to see throughout this presentation is the confluence of Finney Creek with the Skagit Mainstem. But you see that the height distance ratios of less than 1, shown here in this yellowish color, tend to be towards the outer periphery of the buffer, and sometimes close to the stream, but pretty dependably on the outskirts. Whereas the functional wood in height distance of 1 is barely functional, but by the time you get up to 2, 3, or 8, you've got the potential to contribute quite a bit of wood, say in these tributaries and side channels. So this is available for the whole Skagit, and you can browse around and see where the riparian zone is lacking. You could see some of that from an air photo, but you wouldn't quite get the same effect as the height distance ratio. Looking at this data across the whole watershed, out of this overly complex graph, I want to point out a few things. Your height distance ratios of 2 through 8 are shown down here with these progressively further curves. But these have been summed up to what I call the sum of the functional wood, represented by this magenta colored line here, whereas the non-functional wood is represented by this orange line here. And what you see is, although adjacent to the channel, distance from the channel on the x-axis, the area of pixels on the vertical axis, what you see is, adjacent to the channel, you've got quite a bit of really functional wood. But by the time you get out to about 50 meters, you've sloped off to very little. That's why I'm showing you the 150-foot buffer results instead of the 300-foot buffer results. But the non-functional wood, by the time you get out to 50 meters, is pretty much most of the riparian zone. But here's the kicker. Adjacent to the channel, there's a lot of non-functional wood. These are your bare areas and your recently eroded, vegetated, recent cobble bar areas that but also the areas that really need the most restoration. Looked at the exact same data according to land use, what you see is that in the agricultural and the rural residential zone, and these two zones look really similar when you're driving through them. But comparing those to the commercial forest and the federal forest by acreage, you see that for the height distance ratio of 1, the ag zones are proportionately more non-functional riparian stands compared to the forested areas. And the forested areas have proportionally more, and as far as gross geographic area, more area in the functional categories of 2 through 8. So what this graph says to me is that to succeed in riparian restoration, these areas in the forests tend to be further away from the channel, whereas these areas in the ag lands are distant from the channel, but a lot of these are close up and adjacent to the channel. And this is the part that's going to have to be fixed to get some decent shade and large wood in those streams. And I'm going to get off my soapbox now and switch to the shade model, which used exactly the same inputs. That is a full canopy height model within the buffer. And again, did this at 150 feet and 300 feet. Full canopy within the buffer, bare earth elsewhere. And what I did was I used the same ArcGIS hillshade routine that many of us have used, the same tool, but varied the angle of the sun for each hour of the day on the longest day of the year. So a hypothetical cloud-free June 21st. Use the hillshade to look at where would the shade be at 6 o'clock in the morning, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4. You get the idea. Throughout the day, looking at where the shade falls on the stream, and then these black pixels and these gray pixels can be added up. And here's a weakness of the approach. It makes it simple and accessible for a lot of people, but all the hours are counted equally, and that's not quite accurate in terms of heat load. If we were adding up kilowatt hours per hour, we would be counting the noon hours, the middle of the day hours, more than the early and later parts of the day. That's not happening here, but it still gives you a really intuitive sense of how much sunlight is falling on the stream, and then you can sum all those up. So here the scale is from 0 in cyan to 16 hours a day in magenta, and you can see that the east-west reaches of the Mainstem, even though they will never be in full shade in the center of the stream, no matter how much you grow your riparian zone, they get a lot more sun than the north-south reaches. And of course, the tributaries, the closer they are, the more shade they're going to be getting. So this shows you where the sunlight is falling on the stream, but it doesn't necessarily show you where you get the greatest benefit of riparian planting, where you would get the greatest change, the greatest growth. To do that, I looked at the DNR Site Index, and granted there are lots of caveats and cautions about how to use this data, but basically taking the site index, which gives you the height of what's considered a site potential tree in each of these polygons, and clipping those to the existing current watershed, which is a trick and probably 5 or 6 more slides that I'm going to skip over, but created a new input model where the height of the buffers along the channel are equal to, are a site potential tree height, and then rerunning all 16 of the shade routines. And by the way, I've got a script that runs them all pretty automatically. It's a fairly simple script. I can make that available to people. But Ray running all 16 screens. And before I go on, I have to stop and remind people, the DNR Site Index does not cover the whole watershed. It does not cover federal lands. So what I'm going to show you from here on out is going to be limited to non-federal lands, the comparison with site potential tree height. So with the new input model and the running the shade routines again, you come up with a sum of shade, sum of sunlight on the water that's quite a bit shadier, quite a bit cooler. And then it's a pretty simple matter of subtracting that from the sunnier version in from the 2016 LiDAR. And the difference is going to show you where you get the greatest change between current conditions and optimal conditions of a site potential tree height uniformly everywhere. So I'm hoping that this sun difference raster can be useful to you folks in trying to pick out some opportunities for riparian restoration throughout the watershed. Now, taking that data and piling it in, compiling it, what you see over the whole watershed is, and again, this is hours per day on the horizontal axis versus the area exposed on the vertical axis. You see a lot of areas that were getting 14, 15, 16 hours a day of sunlight shrink down, and the areas that are only getting 0 to 8 hours a day are commensurately greater. Overall, an 18% improvement in shade over the whole watershed, and quite a bit more of the areas getting less than 8 hours a day. Now, this is for the whole study area, non-federal lands in the Skagit and Samish. When you limit that to just the tributaries, you see a very different pattern but a much greater effect as more areas go from more hours to bigger areas with far fewer hours, the 0, 1, 2, 3 hours per day, quite shady. Oh, an overall 90% reduction in the major tributaries. So I'm hoping those results are helpful for folks. Before we move on, I want to acknowledge that the initial shade model idea came from Mike Maudlin, Ann Stark, and Victor Johnson at the Lummi tribe, who did this the first time many years ago. And then Gus Satius and Kate Ramsden helped a lot with the single thread hydrography. And if I did that right, then we should have plenty of time for questions.
The first question is, the channel polygons look great. Have you compared your outputs to the channel polygons, surface water polygons produced by the WDF&W HRCD-HRLC mapping? I am guessing the relative elevation model based approach could potentially reduce the shading issues for the surface water mapping approach. Thanks.
Yes, Ken Pierce and I have been back and forth about this. The method I used is pretty labor intensive, but it sees the channel banks underneath the overhanging vegetation, and the HRCD does not. You're capturing the overhanging veg, and that isn't such a big deal on the big wide main stems. But what you find is that those middle-sized tributaries, the Jackman Creek, the Bacon Creek, Day Creek, those tend to get occluded by vegetation pretty quickly, and you're just looking at trees. You can't see very far up the channel with the air photo method. but you can with the LiDAR method.
Okay, the next question is, how do you deal with floods and wind which take down site potential trees in the riparian zone predictably?
I'm not sure how predictable that is. Certainly there's, riparian zones are highly dynamic. We all know that. And this is a snapshot in time. I probably should have mentioned that although a lot of the trees further away from the channel aren't contributing a lot of wood now, it doesn't mean that they won't over time. Those will grow. This is a snapshot in time based on the 2016 LiDAR primarily. And it's, I think it's pretty amazing to me how yet some reaches change a lot. Most of them don't change as much as I assumed. So I think it's still pretty accurate, pretty relevant in most areas, if not, the middle of the Sauk River, which jumps around quite a bit, and some of the larger tributaries as well.
The next question is, with the shade model, the CHM is treated as impermeable to light when using hillshade function, right?
Good point. Yes, it's impermeable to light. I've tried using point clouds and leaf area index to shine light through the canopy, the riparian canopy. But a couple of things make that difficult. One is there just aren't very good tools. There aren't very good algorithms or routines or whatever you want to call them to do that. And B, the Skagit LiDAR was shot leaf off. So even if the digital routines, the code, the R code worked better, you'd still be shooting light through a bunch of bare alder, and you wouldn't be getting a very good depiction of what the canopy is truly letting through. I spent a fair amount of time this summer taking hemispherical photographs in a lot of these tributaries, and the correlation between what you see in a summer photograph and what you get from a LiDAR point cloud is quite different, very different.
What is the criteria for a major tributary?
I should have come up with a metric for that. It was, I excluded the Mainstem Skagit, the Mainstem Sauk, the Mainstem Cascade, but I included, and it was, I probably should have been a little more precise about this. I included Dataset Creek, Bacon Creek, Jackman Creek, Day Creek, the larger tribs, the White Chuck, areas that were, not so wide open that it was guaranteed that they would get full sun in the middle of the channel, no matter what. I do have a GIS layer of where I did that clip. I can go back and review that for you. If you want to email me, I can clarify that for you a little later.
The next question is, are you considering tree growth in the height distance calculation?
No.
Trees that would not contribute at age 35 would be much taller at age 100 plus and could contribute.
Sure, absolutely. Well, that is what the site potential tree height is meant to capture, is trees going from the current condition to the optimal site potential tree height condition. I did not attempt to grow trees. I simply leapt to the site potential tree height.
Thanks, Tim. Great work. Can you speak to difference between HD ratio and absolute height of trees and function as potential wood in adjacent channel?
Yeah, since I put this most of this together, I did go through and I looked at height minus distance instead of height divided by distance. And I came up with a graph that looked remarkably like the one I showed you height distance ratios, but it was a little harder to get the axes right. And so I didn't include it here, but you get a real similar result when you're looking overall at the basin. Probably needs to be explored whether you see minor differences in the changes when you zoom into the landscape. Haven't done that yet.
Is the new hydrography, the single thread and the polygons publicly available?
Not yet. The single thread is close. I just did a first draft on the metadata last week, and it's under internal SRSC review, and we should be able to put that out pretty soon. The channel polygons will take a little longer. Again, for other people who want to, for practitioners, I think you can probably get a lot of what you need off of the rasters, the difference between the 2016 and the site potential tree height. For other folks who want to do similar techniques in their own watersheds, get a hold of me and I can help walk you through some of the scripts. There are lots of them that do a lot of this work automated.
I did find one other question in the chat. Can you clarify your point about types of trees that provide shade? Were you able to determine conifers versus deciduous in your model? I think you were alluding to large difference in shade. Is that correct?
There's a large difference in shade because the LiDAR was shot leaf off. So there's a huge difference between the broadleaf trees, the cottonwoods and the alders and the conifers during leaf off conditions. And then to do a better analysis using the LiDAR point cloud, you would need to have leaf on LiDAR. There are a couple of papers out there that allude to being able to correlate the two close enough, and that's why I pursued it. But turns out I couldn't get a good correlation. So I'm not, yes, much different shade during leaf off conditions, but not so much during leaf on conditions.